Good afternoon. Today we will be discussing about remote sensing application to marine and atmospheric environment. So I will be covering here about the passive as well as active microwave sensors and their applications both in marine and atmospheric environment. We will be
This conference will now be recorded.
we will be discussing about the basic principles and the applications. So, what can be measured by satellite sensor? These basic 4 parameters are normally measured by a satellite sensor, that is color of the object and temperature of the object and slope and height of the surface and the roughness of the surface. These 4 parameters give you a lot of information about the ocean surface. So color of the ocean will tell you whether the water is clear or turbid and what type of biological substances present in the water. And temperature of the surface will give you information about the warm currents, cold currents, or the upwelling, which brings a lot of nutrient-rich water to the surface, which are cold in nature. And apart from that, when you will go to get the information about slope and height, you will get the information about the geostrophic current and the what do you call the sea surface height anomaly information and the roughness of the ocean, because the normal wind roughened sea means if wind is there, sea will get roughened, and so the roughness information can give you how much wind is present over the ocean. So to measure the basic color, temperature, slope and height and roughness, etc., we have sensor range of sensors, not one sensor. So the satellite sensors are categorized in 3 groups, mainly visible and near infrared, and then thermal infrared and microwave infrared. So the wavelength range of visible and near infrared is 0.4 to 0.8 micrometer, and the utility is to study the ocean color, and in the atmosphere you will get the information about aerosol optical depth, which is nowadays being used to estimate the air quality. And thermal infrared will give you information about the sea surface temperature, and the wavelength range is around 3 to 12 micrometer. Then comes active microwave sensor, that is 0.3 to 30 centimeter, which gives you information about sea surface roughness, slope and height, and all other atmospheric parameters. So one by one we will be discussing, and we will start with the basic physical principles, then we will go to the applications in each topic. So in this slide, what you are seeing is color of the ocean, and you can see different color. One is blue in nature, and another is greenish, and somewhere the bottom reflectance is visible, and so bottom material you can find out, and somewhere the sky reflectance also coming in this horizon. So while you are sailing across the ocean in the near shore waters, you will find water is greenish, and as you are going further, the watercolor will change to blue. So why this color is changing? So this is the first paper published in 1922 by Sir C.V. Raman on the molecular scattering of light in water and color of the sea. So this was the beginning of ocean color study when the satellite remote sensing was not there. Nobody thought of utility of these investigations for monitoring the ocean environment. So coming to the study of color of the ocean, first Lord Rayleigh, he explained the blue color of the sky, it is due to the molecular scattering. So the air molecules will scatter blue light more compared to other wavelengths, that is green and red. As you know, the sunlight is comprised of 7 colors and in the visual wavelength range. So blue light is scattered more, and that's why we are seeing the blue color of the sky. So he attempted to explain the blue color of the ocean, and he explained that ocean is looking blue simply because of reflection. But Sir C.V. Raman explained that the blue color of the ocean is not due to reflection, but due to scattering of water molecules, the same way air molecules scatters the sunlight. So the light which is penetrating into the ocean, the water molecules, they scatter blue light more compared to other wavelength, then show ocean color is looking blue. But as other substances will present where blue light will get absorbed, those wavelength region means those waters other than water molecule means in the coastal water the color will change to green. So this slide shows you the absorption and backscattering characteristic of water molecule. So the water absorbs very less. The red line represents absorption coefficient, and it absorbs very less light in the blue wavelength region compared to red wavelength region. And the reverse is true, means backscattering is more in the blue end of the spectrum compared to red end. That's what in the pure uncontaminated water you will get scattering more in the blue end of the spectrum and absorption is less. So you will get high reflectance in the reflectance spectrum of the pure water. So you will get a reflectance spectrum like this, where the blue wavelength will reflect more compared to red wavelength. So there is a simple relationship between the subsurface diffused reflectance and the scattering and absorption coefficient of the water. So the scattering and absorption coefficient of the water is known as the inherent optical properties. So they are related to the reflectance of the water, and the reflectance of the water will tell you whether the water is blue or it is green. So from that you can derive inference about the substances present. So these are the main 3 substances which are responsible for changing the ocean color. One is phytoplankton, and another one is suspended sediments, and the third one is dissolved organic matter. So the phytoplankton, the phytoplankton is a microscopic plant which is floating in the water, and this you can see from the images they are having different shapes, sizes, so they scatter the light accordingly, and this phytoplankton are grouped as diatoms, and they have siliceous cell-like cases, and they have the photosynthetic pigments. So these phytoplanktons in the ocean environment, they live for around means 24 hours, and when they die, they settle down to the ocean bottom, and they form the diatomaceous ooze. And these are coccolithophores. They are found in the oceanic desert waters, and they have a calcareous plates, and they thrive in the nutrient poor water. So these are dinoflagellates, and two thread-like structures are present. That's why they are called dinoflagellates. And some are responsible for harmful algal bloom. So these phytoplanktons, they absorb the blue light more compared to the other wavelengths. So let us now study about the absorption and scattering characteristic of phytoplankton. So this green line shows you the absorption coefficient of phytoplankton, which shows you the peak in the around 445 nanometer, which is at the blue end of the spectrum. So, and there is another peak, it is in red end. And there is no definite shape when compared to the where you are analyzing the backscattering coefficient of phytoplankton. You cannot find a definite relationship. It is somewhat flat here, and dip here, dip here. So unlike absorption coefficient, which is more in the blue band of the spectrum, scattering coefficient has no definite shape, because the shape of the phytoplanktons, they vary. So it is the scattering coefficient is not following any pattern. So taking the absorption coefficient of phytoplankton adding to the water molecules. So wherever the phytoplanktons are there, the water absorption will be more in the blue end of the spectrum. So you can develop a biooptical algorithm. So what you have to know to develop a biooptical algorithm is you have to study the inherent optical properties of the water molecule, as well as the chlorophyll, means phytoplankton that is present in the water. So you will study the absorption and backscattering characteristic of the substances present, and you will relate these inherent optical properties to the reflectance of the water. Then inverting that model, you will get the constituents present in the water. That's what we are implementing these algorithms to retrieve the substances present from the present in the water from the radiance or reflectance that is determined from the satellite sensor. So this graph shows you how the reflectance spectra of the water varying with varying phytoplankton concentration. So this is the phytoplankton concentration is changing from 0 milligram per meter cube, that is clear water, to the water having 5 milligram per meter cube. So what you are seeing, where it is 0, the reflectance is very high, and slowly it is going down. So water color is blue. When the chlorophyll is changing to 0.5 milligram, the water color is means blueness is decreasing, and for 1, 3, 5, etc., the blueness is totally decreasing. But there is a hinge point at 550 nanometer. So if you take the ratio of blue to green channel, you can relate how means you will find, you can estimate how much chlorophyll is there in the particular water. So this is the basic of finding out means applicability of the bioptical algorithm. So we call it pigment index, that is defined as R lambda 1 by R lambda 2. So lambda 1 represents blue wavelength and lambda 2 represents the green wavelength. So you can relate this ratio later to the pigment index, that is chlorophyll concentration is related to pigment index through regression, and A and B are the coefficients of regression. Nowadays, you will get the sophisticated bioptical algorithms having logarithmic and many coefficients. Then we will discuss about now how the ocean color data is being processed. So first of all, we take the satellite data and perform atmospheric correction, because ocean only emits 10%, contributes 10% to the total radiance received at the satellite sensor, and rest 90% are contributed by atmosphere. So atmosphere is having air molecules as well as suspended particles known as aerosol optical depth. Apart from that, ozone and carbon dioxide, etc., means the some absorbing atmospheric gases will absorb the incoming as well as outgoing radiation, so affecting the transmittance of the atmosphere. So after doing atmospheric correction, you will retrieve the radiance, that is upwelling radiance coming from the water, from below the water. And once you have a suitable bioptical algorithm to retrieve a geophysical parameter like chlorophyll or suspended sediment, etc., you can apply to the atmospherically corrected satellite data to get the water quality parameter. So what is happening? The sun during daytime, you can study the ocean color. So where sun is the source of light that is falling on the ocean surface, and it is penetrating to some depth in the ocean, and due to absorption and backscattering, the upwelling radiance reaching the satellite sensor. So this upwelling radiance coming out of the ocean carries the information about the ocean. So what is happening when light is falling on the ocean surface? Part of it is getting reflected back to the satellite sensor from the surface, which is known as Fresnel's reflection or specular reflection, and rest of the remaining light will enter into the water column, and while passing through the water column, it will get successively absorbed or scattered, and the backscattered radiance will be reflected back to the water medium in the following the principle of Fresnel's reflection coefficient, and the remaining light will pass through the atmosphere and reach at the satellite sensor, which we call LW. LW is nothing but the water leaving radiance, which is the oceanographer or ocean color researcher they are looking for, and they will relate the LW to different biological parameters of phytoplankton or suspended sediment or dissolved organic matter, etc. So apart from LW, two more parameters that is reaching the satellite sensor are LR and LA. So LR represents the molecular scattering, and LA represents the aerosol scattering. So all three parameters they reach the satellite sensor, so constitute the total radiance received by the satellite. So you have to remove LR and LA from the total received energy to get the radiance due to water leaving radiance, that is LW. So this is known as atmospheric correction. So in the atmospheric correction part, we are removing the LR and LA. So there are radiative transfer models and specifically designed for the satellites, and it is provided by the space agency, to correct the raw satellite data and to retrieve the water leaving radiance. Later on, the water leaving radiance can be utilized by the suitable biooptical algorithm to derive yellow substance, chlorophyll, or suspended sediment, etc. So I am providing you about the ocean color monitor, which is present in OceanSat 1 and OceanSat 2. And in future, OceanSat 3 also will come. And these bands means in OceanSat 1 and 2 bands are almost same, but little bit variation is there. And OceanSat 3, some more additional sensors will be there. So here the 8 bands are there, and the central wavelength is 412, 443, 490. So this first band is used for determination of yellow substance and turbidity, and the middle 3 bands are used for retrieval of chlorophyll concentration. The first 443 is used for the retrieval of chlorophyll where it is very low, that is in open ocean area, and medium chlorophyll is in between the open ocean and coastal waters, and high chlorophyll normally it will be found near the coast, that is 510 nanometer. So and 550 nanometer will be used as a hinge point for pigment index generation, and 550, 620 both are used for determination of suspended sediment, and 740 nanometer and 865 nanometer are used for atmospheric correction. So these are the application of visible remote sensing for monitoring marine environment, that is seasonal mapping of phytoplankton. So I will show some of the global pictures that are available, and detection and monitoring of phytoplankton bloom. So how we can detect a bloom even without atmospheric correction, that we will discuss, and the quantitative determination of suspended sediment, and ocean and coastal circulation, surface currents, and transport and freight of marine pollutants, oil slicks, etc. And estuarine studies like coral reef bathymetry. So for this, high resolution and hyperspectral sensors will be mostly used. Then this picture shows you the oceanic EDs, that is means you can see the small EDs, and this is the Arabian Sea, and this is the Barents Sea, and normally when you are in the ship is just a dot in the ocean, so you may not able to see the beautiful EDs, and in the satellite this is can be identified very precisely. And this is the raw image. CWIPS is another sensor which was launched on board Sea Star for studying the ocean color, and it has provided a lot of data. I will show you one animation generated out of CWIPS, and this is the raw image, the means true color image, and the white is cloud patches. And after doing atmospheric correction and applying the biooptical algorithm, this image is converted into the phytoplankton image. So the red color showing the high chlorophyll concentration which are normally confined to the coastal area, and the green patches show you the medium chlorophyll concentration, and the blue patches are low chlorophyll concentration. So after doing atmospheric correction and applying the water quality means geophysical algorithms, it is converted into the phytoplankton map. So this is from MODIS, another sensor which is on satellites Terra and Aqua to study the ocean color, and it is LW represents the water living radiance, which is used for almost all parameters, and this is generated using the LW, the chlorophyll map, and aerosol optical depth over the ocean is derived from 865 nanometer, that is in the infrared portion of the electromagnetic wavelength. And this is the detection of algal bloom, trichodesmium bloom observed on Saurashtra coast during month of May, and this is from IIRS P4, that is OceanSat 1 data. And this is the OceanSat 2 data, the false color composite image, and shows you it is near the coastal area of Goa, and this is the land portion, and this portion is enlarged here, and you can see the EDs and showing you the phytoplankton patches. Without doing any atmospheric correction, as the phytoplanktons have expressed themselves in the surface, showing the blooming condition, and easily you can detect these blooms, and this can be forecasted, means information can be given to the fisherman community not to go for fishing to this area, because this blooming area may be very toxic in nature for fishes. And this is oil slick detected by the MODIS data. And this 4 images, global images, show the winter climatology, that is phytoplankton concentration around the globe, and summer climatology, spring climatology, and autumn climatology. So what you have means you carefully, if you will analyze these images, you can see the phytoplankton concentration when in winter sun is in the southern hemisphere, and the phytoplankton concentration is more in these waters compared to summer. Summer it is blackened. So because sun has gone to northern hemisphere, so phytoplankton concentration in northern hemisphere is more in the summer season. Similarly, spring climatology and winter climatology, autumn climatology are giving you different pictures. And one striking feature you can see here, the blue patches, they are almost constantly present in the all climatological atlases, because these patches are called the oceanic desert area. So though sunlight is available for phytoplankton growth, you need 2 parameters. One is phytoplankton, means one is nutrient, another is sunlight. So sunlight is plentifully available in this region. This is tropical region, and easily available sunlight, but nutrients are limited, because to get nutrients you should have upwelling in this area, or well mixed water should be there, so that the subsurface rich nutrients should come to the surface. But as this is absent in the areas only, you can see in the equatorial region the phytoplankton concentration is more, and other region, the means where equatorial region, the ocean turbulence is more, upwelling is more. That's why you are getting a lot of nutrients along with the sunlight. That's why equatorial region you are getting more phytoplankton compared to the oceanic desert areas. So this is the winter climatology in detail. So you can see the oceanic desert areas and the equatorial zone, and here for the means due to winter convection, you are getting here winter bloom in the Arabian Sea, and during summer due to southwest monsoon in the Somalia coast, you get a lot of upwelling and phytoplankton, more phytoplankton growth takes place in this region. So this type of information is means you can correlate with the climatic condition and local climatic condition of the area, or you can also study long-term climatic variation, the effect of climatic variation. If you take the decadal data observed by the satellite. So this is the 10 years CWIPS data showing the phytoplankton over the ocean from January to December, and as well as the normalized reference vegetation index over the land. So this picture shows you the effect of El Nino and La Nina. So you know the El Nino condition, the productivity will become very less, and in La Nina condition, it will be very high. So in January 98, you will see El Nino condition, so the productivity is not there and very less. And in the La Nina condition in July 1998, you have very good productivity. So this type of information can be easily inferred from the ocean color studies. So apart from that, the phytoplankton, which assimilates the carbon present in the water, and when they die, they sink to the ocean floor. Thus, they remove the carbon from the ocean. So, as you are aware of the greenhouse effect, and steadily the carbon concentration in the atmosphere is increasing, and the ocean water absorbs the carbon, and the phytoplankton, when they are dying, they remove the carbon from the surface water and sink to the ocean bottom. So if you can estimate the primary productivity of the ocean in a continuous basis, taking the means some surface to euphotic depth and the sunset to sunrise time, the column primary productivity can be estimated, and presently the satellite derived phytoplankton concentration is being given to the model like vertically generalized primary production model, and the column primary productivity is being carried out globally. And this is the historical estimates of ocean primary production, that is from 1968 to 1998. So this figure, Martin et al. 51 and 48.5 gigaton of carbon per year, almost equal to the productivity that is being carried out from the CWIPS. So this is the VGPM model output, how the primary production distribution around the globe from 1997 to 2002. Then this primary production means this information are used to study the carbon budget of the globe. Then coming to remote sensing of coastal waters. Coastal waters are normally optically complex water because the optical properties are there are diverse substances are found in the coastal water whose optical properties are less known, not studied much. And apart from the phytoplankton, you have bottom reflectance, you have inorganic suspended sediment reflectance, and you have bottom flora, and all these reflectance are reaching the satellite sensor. So to segregate each one of them, it is very difficult and active area of research. So now we will discuss about the absorption and backscattering coefficient of suspended sediment. Where I have given you example of absorption and backscattering characteristics is observed in the coastal waters of Paradip, and you can see a U-shaped absorption coefficient and a convex backscattering coefficient. When you take and add to the water, you will get a reflectance spectra for varying suspended sediment concentration. So if you have different satellite bands, you can directly relate the reflectance to the suspended sediment concentration. So here some relationship, how reflectance is varying with suspended sediment at different wavelengths. This triangular line shows the reflectance at red band, and this shows at the green band. So the relationship is linear when you are finding out, going towards the red wavelength range, and when you are moving towards the blue wavelength range, it is becoming non-linear. So you have to take care of that. So what you have to do, you can go for a synchronous study, see-truth data collection, and here we have given an example. We have taken IIRS 1C WIPS data and developed a bioptical algorithm relating suspended sediment concentration to the reflectance that is observed at the red wavelength range. So then this image is converted into the suspended sediment concentration map, and this is the Paradip river bringing a lot of sediments to the coast, and this is the Paradip port. And these are the suspended sediment seen by other satellites. This is the true color image, and you can see the pattern of suspended sediment concentration confined to the coastal area. And this is the coastal circulation and plume dynamics as observed by OceanSat 1 data, and superimposed the QuickScat data and the sediment pattern, how it is being affected by the wind direction. And these are the suspended sediment pattern. They are not only confined to the coast alone, they go deep inside the ocean, and some of the interesting pictures are being captured by the OceanSat 1 data. And this is the suspended sediment climatology generated of Kakinada coast, taking 5 years data, and you are getting January, February, March, and April, June, July, August data is missing here due to the cloud cover. Normally, this is during the monsoon season. You will not get the data. Whichever data is there, it is cloudy. So then this is the climatology generated from the OceanSat 2 data, which is showing the suspended sediment concentration near the Kakinada coast. And this is the phytoplankton concentration map generated from MODIS data, which is showing the coastal plumes means phytoplankton concentration and open ocean phytoplankton concentration from January to December. Then coming to the thermal remote sensing, these are the application of thermal remote sensing, and one, you can study the climatology and global change in SST, weather prediction, gas exchange across the air-sea interface, and dynamical oceanography and pollution studies. So the thermal sensor means it is easy to understand, and the radiance that is received by the satellite sensor, normally people get confused about the reflectance and emission. Any body is having temperature that will emit the radiation. So if you have a thermal sensor, both day and night, you can sense the emitted radiance from the ocean surface. So both day and night, you will get the sea surface temperature information. And the radiance, what you are getting is m lambda. And if you will put it in Planck's law and invert the Planck's law, you can find out the temperature T of the object. So we have several satellites having the thermal sensor, high resolution to low resolution, means starting from a few meters to you have kilometers together. So this is the a geostationary satellite, Kalpana 1, which is having a thermal sensor which gets the sea surface temperature data. And this is the MODIS Terra, is also having thermal sensors and also providing the, so these are two synchronous passes around the same area. So the temperature are quite matching with each other. And MODIS Aqua also gives you the same impression. So the it is resolution is high here, it is low here, and this type of data. But the advantage is every half an hour you will get how the temperature is varying over the locality. And this is the MODIS sea surface temperature data over Bay of Bengal, how it is varying from January to December. It is generated from the MODIS satellite data. And this is the climatology of sea surface temperature, winter climatology, summer climatology, and spring and autumn. So this is the winter climatology when sun is in the southern hemisphere, and you have low temperature in the Arabian Sea, and as you are moving to summer, the temperature is in Arabian Sea is increasing, and a low temperature in the southern hemisphere, it is becoming more. And other than the climatological studies, the sea surface temperature data can be used for detection of potential fishing grounds. That is, wherever the phytoplankton is more, the zooplankton segregate and fishes consume the zooplankton. So the high primary productivity area or the area having high phytoplankton concentration will give you an idea of potential fishing grounds. So apart from that, when two water masses mix, they give a color front and a ocean front also, means a thermal front also. So the thermal fronts can be easily detected by the satellite for demarcation of PFZ area, and the oceanic rings and the EDs and the front areas and meanders and upwelling areas can be segregated. These are the enlarged view of the parameters, and these are the rings, and these are the coastal upwellings, and the rings are formed due to the ocean dynamics, and the coastal upwellings are formed due to coastal dynamics and the surface wind condition, etc. And these EDs and upwelling features can be extracted and supplied to the fisherman community for going to the particular spot and identifying the potential fishing zone. So this is the NOAA data or any other satellite data having the thermal bands. You can extract SST, and the ocean color data can be derived from the ocean color sensors, and this will give you phytoplankton concentration, and SST with phytoplankton concentration. You can do the analysis and generate a potential fishing zone map. So the Indian National Center for Ocean Information Services, they provide the potential fishing zone advisory to the coastal areas in a regular basis, and these frontal zones are being utilized by the fishermen community to go for fishing. And apart from the SST data, the ocean color data is being used, and wherever the ocean color front is matching with the thermal front, the fish catch is found to be more in those areas. This type of R&D studies are being carried out by the investigating agencies, and Indian Council of Agricultural Research is a part of it. And the overall it is the PFZ mission, and the satellite data is being utilized to generate the PFZ maps, and dissemination is carried out through multilingual maps, text, and fax, phone, etc. And the fishermen, they get easily the information, and they give their feedback to improve the R&D efforts and modeling, to improve the modeling technology, etc. And we have achieved around 70% success rate in predicting, for potential fishing zone detection. So I will not go in detail about the classification of coastal zone using high resolution satellite data. It will be covered in another lecture. So this is the high resolution satellite data, and that can be used to demarcate classify the coastal area. And one of classification and site suitability for pearl culture farming was carried out in the Minicoy Island. So this is the map generated for the site suitability map, and this is the underwater coral observation, and these are the mapping carried out by utilizing the high resolution satellite data. And now coming to the microwave remote sensing of ocean, it is segregated mainly in two parts. One is passive microwave sensor. Passive microwave sensor is utilized to get the sea surface temperature, wind speed, sea surface salinity, etc. And the active microwave sensor, we have mainly three sensors. One is scatterometer, which provides you wind speed, wind direction, and altimeter, which gives you significant wave height, wind speed, sea surface height anomaly, geostrophic current, etc. And synthetic aperture radar SAR tells you about presence of oil slick, a wave spectrum, coastal bathymetry. So we will touch upon each one. And coming to passive microwave, it follows the same principle as thermal remote sensing. Only assumption of Rayleigh's approximation is applied to Planck's law, and here the sea surface temperature from advanced microwave scanning radiometer, which is present in the Modis Aqua and Terra. They are capable of penetrating the cloud. So in presence of cloud also, you will get the sea surface temperature. So this is the temperature as detected by the MSRE. And this is the sea surface wind speed from MSRE, passive sensor that gives you the sea surface wind speed over the ocean from January to December. And the passive sensor, that is 1.43 gigahertz channel, that is being placed in several satellites to give you the sea surface salinity information. This 1.43 gigahertz is found to be more efficient compared to 2.65 gigahertz channel. So you can, for different sea surface temperatures, the brightness temperature at 1.43 gigahertz is found to be different. So for zero salinity, you get high brightness temperature, and when for high salinity, you get low brightness temperature. Of course, it is again varying with the prevailing sea surface temperatures. So this monograph gives you the information how sea surface salinity can be detected. So you have the SOM sensor, SMOS, that is soil moisture and ocean salinity. So it has given you a global view of the salinity map over the ocean. And this is the NOAA NODC means sea truth collected data compiled to give you the sea surface temperature, sea surface salinity information. And this is from SMOS, satellite measured salinity information. Here, another satellite, Aquarius. This is also having 1.43 gigahertz passive microwave sensor, which has given the sea surface salinity information around the globe, where you can see normally the Arabian Sea salinity is more compared to the Bay of Bengal salinity. And this is the SMAP, another sensor that is giving you the salinity information. Then coming to active microwave sensor, first we will discuss about altimeter. Altimeter sends a pulse to the ocean surface and measures the return pulse. So the height of the sea surface can be determined. That is called range of the satellite. So the satellite orbit gives you the altitude of the satellite, because the satellite is rotating in its orbit with reference to the ellipse of the ellipsoid, a mathematical surface of the Earth. So the ellipsoid is known, and the height of the satellite from the ellipsoid is known. So the altitude is known. So when you are getting this range and two parameters are known, then sea surface height is easily found. That is sea surface height equal to altitude minus range. So it gives you sea surface height, and it helps you to give the this picture shows you the range, that is from sea surface height to the satellite sensor. So it is instantaneously measured, and altitude, it is the reference from the distance between ellipsoid and the orbit. So from these two parameters, sea surface height is known. So if you know two different heights, you can find out the slope of the sea surface. So water will flow from higher slope to lower slope. So this will give you information about geostrophic current. So normally, and this shows you the basic principles of satellite altimetry. So a pulse is sent to the ground, and if the sea surface is flat, you are getting a return plus a flat shape curvature. So if the sea surface is never flat, it is a hypothetical surface, but the actual sea surface will be rough, and you will get a instead of a flat response, you will get a shape like this. So this is the return signal. So it is depending on how much rough is the sea surface. So indirectly, it will give you information about significant wave height if you will average it out. So you can relate it to, so if this is the average of 25 ecos, and this is the single eco, and if you are taking average of 1000 ecos, you will get a perfect shape. So the slope of the leading edge will give you the information, means you can relate the slope of this leading edge to the significant wave height. So for different significant wave heights, that is A, slopes are different, and B, it is here, C, it is here. So from these slopes, this shape of the altimeter waveform, you will get the significant wave height information. So already we have discussed at two places. If you know the sea surface height, you can find out the slope of the sea surface, and water will move from higher slope to lower slope, and it will get deflected by the Coriolis force of the earth towards right in the northern hemisphere and towards left in the southern hemisphere. So you can find out the geostrophic current. Then the sea surface height information can be utilized to get the sea surface height anomaly. So there are many altimeters present in the different satellites which give you range and sea surface height and backscattering, normalized backscattering coefficient and sea surface height information. So these I am not going through in detail. There are GOES, CSAT, GeoSat, earlier having the altimeter in their payload, and now Saral Altica. It is a project collaboration between France and India, and Altica is having a car-band altimeter, and it is dedicated to accurately measurement ocean surface. It is also known as coastal altimetry, and these are sea surface height anomaly from the Altica. And you can take the sea surface temperature data and chlorophyll data from phytoplankton, means ocean color data, phytoplankton information, and you can take the sea surface anomaly data from the altimeter, and three things can be was combined together to detect the potential fishing ground for tuna. So this type of studies are being carried out globally, and this is one of the utility of the thermal ocean color and microwave remote sensing. And the you are already aware of principle of radar remote sensing, means a pulse is sent to the ground, and if it is a house and if it is a tree, and you are getting the return pulse first from the house and second from the tree, and the distance and strength will give you information and characteristic and distance of the object. So this is the principle used for getting the backscatter, and same means this is the principle of scatterometer, and it is a conical scanning sensor that is getting the sea surface backscatter from in different polarizations. So the SCATSAT-1 is launched by ISRO in 2016, which is presently in orbit and giving you the backscatter information. And the backscatter information will tell you, means this graph shows you the backscatter data for different wind speed conditions, and for different polarizations it will be different. So from this information, backscatter information, you get the wind speed and wind speed direction from the scatterometer data, and the data is available in National Remote Sensing Center. Some are in free of cost. You can use this data, and this is the path of the scatterometer. It shows for one cycle around, and these are the some of the products which is showing the wind speed and wind direction during the cyclonic event that are being observed by the ocean chart means scatterometer. And this is the snapshots of high resolution winds captured by SCATSAT during cyclone Varda in Bay of Bengal. And these are some of the products generated both utilizing the model and the satellite data. And the MOSDAQ site, it is available. You can utilize the MOSDAQ site of SAC to get more information. And this is the wind speed from the global navigation satellite system, and they send the means it is a GPS signal. Normally it strikes in the ocean surface, and the return pulse is measured, and you can get a high resolution wind speed information from the navigation satellite system. Then coming to synthetic aperture radar, there are now it is having means data you are getting in a variety of resolution and swath sizes, and first we can discuss about retrieval of ocean wave spectra from SAR. So to understand this is the simulated image of a sinusoidal wave, and this spatial image can be converted into a frequency domain by applying the Fourier transformation, and this is the simulated image, and the wavelength is 120 meter, and the direction is 45 degree. So you can put this spectrum, generate this, converting the spatial domain to frequency domain, and you will get the wavelength information and wave direction. So when you will in real time you get the SR data, means wave data, in a similar way you can convert it into the spatial, means frequency domain, to get the wave direction and the wavelength information. So this is continuously being processed and measured all over the globe, and this information can be given as an input to the ocean models. Apart from that, the you can also generate shallow water bathymetry, coastal bathymetry, using the SAR data. So this is the simple principle, that is wherever the means ocean surface currents, when they are feeling the ocean bottom, the surface of the ocean will get compressed, and somewhere it is flattened. So if it is compressed, the sea surface will become very rough, and the SAR image you will get a very light tone, and where it is flat you will get a dark tone. So the bright and dark tone will give you the surface condition of the coastal water. So if you have a the numerical model which can be simulated, means you can initiate the model providing the initial first Gauss bathymetry and the current and the wind over the area, and you can generate a surface roughness from the numerical model, and also subsequently you can generate a backscatter image, simulate backscatter image, and you can compare with the simulated backscatter image with the real SAR image, and by tuning the bathymetry, when these two images will converge, you will get the updated bathymetry. This is the principle being used to determine the bathymetry. This one of the software is bathymetry assessment system, which consists of a numerical model which calculates a synthetic SAR image from a first Gauss bathymetry. The difference between synthetic image and the actual image is minimized in such a way to generate an update of bathymetry. This process repeated until the depth values converge. So this is the summary of that principle, and this is the one of the image SAR image, and after applying the BAS system, you are getting the coastal bathymetry in the near shore water. So another image, it is if a gentle sloping beach is there, and you can use the wave dispersion equation to the SAR data, and you can generate the bathymetry. This is the generated using RISAT data, RISAT-1 data, and this is mostly applicable where the bathymetry is gently sloping. If it is bathymetry is irregular, you have to go for a BAS system. Then coming to LiDAR data, principle is very simple. You have to send a pulse, and the return pulse time you can note down, and from the surface and from the bottom of the ocean, if you know the reflectance, you can backscatter, you can find out the water depth, as well as you can know about the water surface, means substances that are present in the water column. So there are basically two wavelengths are functioning in this. One is infrared laser pulse around 1064 nanometer, and green laser pulse that is 532 nanometer. As you know, infrared will be absorbed by water, so only you will get surface reflectance from the infrared, and the green wavelength will penetrate to the deep, and you will get the information. So the difference between these two will give you the information about the bathymetry. So utilizing means in the aircraft, you can have the two sensors, and you can find out the bottom reflectance and surface reflectance, and the difference will give you the bathymetry information. So these are some of the examples. These are underwater pinnacles, some geological features, and these are nicely mapped. You can see here three-dimensional map from the underground pinnacles. And this is the sunken cargo vessel below the sea surface, measured by the LiDAR data. And this is the channel through a coral reef. And these are the maximum depth up to 60 meter can be mapped, and operating altitude is 400 meter, and the scan width is 220 meter. And the challenges here are summarized: small object detection and identification, seafloor classification, whether it is sand, mud, gravel, stones, or vegetation, and land water discrimination. So further, I have given the website, you can explore. And now we will focused on remote sensing of atmosphere, and where you can study about aerosol, ozone, water vapor, and weather. So aerosol optical depth is defined here, and if you know the extinction coefficient, then integrating over the whole atmosphere, you can get the aerosol optical depth. And if you take the exponential of, you will get the transmittance of the atmosphere. So this is the image from OceanSat-1 and CWIPS and MODIS aerosol optical depths, how they are giving the values. Comparison is being carried out, and they are found to be very efficient. So the aerosol optical depth derived from different satellites can be simulated in the models to study the air quality. So, and this is the aerosol optical thickness observed from the MODIS data over land and ocean for January to December from 2001 to 2006. And in the July means monsoon months, it is found to be high. So this shows the aerosol optical depth is found to be high in June, July, and August season. And this is the absorption cross section of ocean, and you have the UV spectrum. And there is a difference between these two, the visible wavelength range and the ozone cross section in ultraviolet section. So utilizing this principle, you can find out the ozone concentration around the globe, and it is expressed in total ozone, means in Dobson units, and you can find out the ozone concentration around the globe. Somewhere it is high, somewhere it is low, and even if you can, means it is Antarctica, ozone holes are studied, and you can find the ozone hole in 2001, 2002, and 2003. And there are several websites which are giving the means mapping the atmospheric ozone. This is the one of the site, a total ozone mapping spectrometer, and this is the figure showing you the absorption coefficient of carbon monoxide, methane, nitrogen, and oxygen, ozone, carbon dioxide, water vapor. And so different wavelength regions, the absorption characteristic is different. So this is being utilized. If you have a suitable sensor in the satellite, you can get different absorptions. So, so utilizing that, you have measured the ocean, the carbon dioxide measuring satellites, OCO2, and you have the carbon dioxide concentration of the globe. Now the OCO3 is present in the International Space Station, which is giving you the carbon dioxide concentration. And these are the orbiting carbon observatory 2 in detail. And this is the MOPIT, that pollution monitoring the troposphere, and another chemistry transport model, MOSRAT. So comparison between MOPIT of the carbon monoxide population, means pollution, you can find out they are quite matching with each other. One is model output, another is satellite measured carbon monoxide. So already we have discussed about the principles. So this is the atmospheric water vapor. One is showing the absorption transmission is more, another is transmission is very less. So if you are taking information in two different wavelengths, you will get the amount of water vapor that is present in the atmosphere. So this is the MSRE water vapor, MSRE generated water vapor map globally, and this is the Moody's water vapor from January to December and 2001 to 2006. Some of the case studies being carried out. So the water vapor concentration from January to December, how it is varying over the Indian Ocean, it is being studied. And these are the insert pictures. All are aware of these pictures for observing the weather phenomena. And this is the insert derived parameters, outgoing long wave radiation and cloud motion vector, aerosol optical depth, etc. And these are some of the product outputs, that is relative humidity and rainfall and sea surface height, means surge height information, and this is the all you know, means how the geostationary satellites are being used to study the cyclonic events. And the this image showing you the radar sat, utility of radar sat images during the cyclone, and before the cyclone and after cyclone, the water inundated areas are easily mapped. Then Megatropic is an Indo-French joint satellite mission for studying the water cycle, particularly in the tropical convective system. And these are some of the sensors, that is Madras and Saphir and Scarab, utilized for studying different parameters like relative humidity and long wave fluxes top of the atmosphere, and and another is cloud aerosol lidar and infrared pathfinder satellite Calypso, which is giving you information about the vertical structure of the atmosphere. That is, this picture shows you the volcanic plume. So at different heights, aerosol can be mapped out. So it is means same one infrared, one visible sensor is being used. A wavelength is being used to map the vertical profile of the atmosphere. Thank you.